Hello guys, welcome to Mathedelic. Today we're going to discuss the Hahn-Banach theorem. But before we do that, we need to know certain definitions and certain previous results that we would need in order to prove our Hahn-Banach theorem. So let us start with a definition of a sublinear. So let X be a vector space and P be a mapping from my vector space to the real numbers. And this mapping P is called sublinear if it satisfies these two properties. Property number 1 is the triangle inequality, and this is property number 2. If P has an additional property, which is this, then our P is called a seminorm for X. So as simple as that, just have a functional. If it satisfies just two properties, it's called sublinear. If it satisfies these three properties, then it's a seminorm. So far so good. And just like a functional, the seminorm satisfies P of X. So a seminorm satisfies P of X greater than or equal to 0 for every value of X belonging to my capital X. And P of 0 is equals to 0. This is just an additional statement about my seminorm. And if P of X vanishes only for X is equals to 0, then it is a norm for X. Now let us look at the proposition. So the proposition is, let X be a real vector space and P from X to R a sublinear mapping, and X naught be a proper subspace of X. If I have an element which belongs to this set, now what is this set? You can see it by a diagram. So think of this in this way. So if I have X as a real vector space, let's call this X. This is my real vector space. And now I have X naught, which is a proper subspace. So this is X naught. And now I have a small x belonging to the set such that this set. So it is not an element of X naught, but an element of X. So this is where my small x is. And F naught is a linear mapping with the property that this. So F naught is taking elements from F naught. F naught is taking elements from X naught to R, and it satisfies this property. Now what we need to prove is that there exists a capital F which take elements from X naught direct sum span of X to R with F restricted to X naught is equals to F naught and satisfying this property. What is this thing? This is, I take an element from here and I do a direct sum with the span of X. And now I'm saying that I'm extending the definition of my functional, which was earlier defined only on X naught, to a space X naught direct sum span of X. So it's like the first thing we do on our way to prove Hahn-Banach. Let's try to again recapitulate what we are trying to do. So given I have a functional which takes elements from X naught to R, and it satisfies this property that F naught X naught is always less than equals to P of X naught for all X naught belonging to capital X naught. Now what we are saying is that there exists a functional which takes elements from X naught direct sum span of X. So you give me any X which is not an element of capital X naught but an element of capital X. And now I'm saying that this functional takes my domain as this set and maps it to the real number such that this property holds, and as before this property holds. This is what I want to do, and let us see how we would proceed with the proof. So now we define again Define. It's a very important and beautiful word. So what happened? How did we proceed with the proof? So we defined f of x naught plus alpha x is equals to f naught x naught plus c of alpha. And this is my domain space. So my element small x naught plus alpha x is an element of this space. Now we have to choose the constant c such that this property holds, because what were we trying to do? We were trying to extend this functional from my space x naught to my space x naught direct sum span of x. And in order to do so, it has to also satisfy this property. So it also has to satisfy this property. And in order to make sure that it satisfies this property, when I write the equivalent form of this, I have to write it as this, that this plus c alpha is also less than or equals to p x naught plus alpha x. This is exactly what I have done here. So we define it like this, and then my only worry is to choose my constant c such that it satisfies this equation. Now, how do we proceed with the proof? We say that okay, f is obviously linear. This is very trivial. I would leave it to the reader to verify if it's linear. And now let us choose my alpha to be greater than 0. So if my alpha is greater than 0, I would take my f naught x naught to this side. See, this is all I have done. I've taken f naught x naught to that side, divided by alpha, and now my c comes out to be less than or equal to this quantity. So c is less than or equal to this quantity. Now what do I do when I take my alpha to be negative? When I take alpha negative, I do the same operation. But this time, since my alpha is negative, the sign changes. So c has to be greater than or equal to this quantity for alpha less than or equal to 0. And now what I want to do is finding a range of c such that this formula holds. So if I can find a range of c within which this equation is satisfied, then my work is done. And how do I do that? So c was always less than or equal to this thing, which means if I come to look at it, I substitute x naught by alpha to be c, and I say that since c is always less than or equal to this quantity, so c is equals to the infimum of x belonging to z naught of this thing, since c was always less than. And since c was always greater than equal to this thing, then c is equals to the supremum of this quantity, where I took x naught by minus alpha to be my z. Now we see that c1 has to be less than c2 because you see this. So I substitute z1 and z2. So since my f naught was linear by definition, so this was given, I can write it out like this. And now for my space f naught, this thing was always less than or equal to p of z1 plus z2 as given in the question. So if you see this, for all x naught belonging to capital X naught. And now again I can add and subtract small x, and then I can split it again with the help of triangle inequality, and hence I have proven that indeed this quantity, which is c1, is less than or equal to this quantity, which is c2, for all z1, z2 belonging to capital X naught. So what have I done till now? What I have done is something which is very beautiful. What I have done is I got a function null defined on x naught to the real numbers. It's a linear mapping and it had certain property. And now I extended the definition of my linear functional such that f restricted to x naught is equals to f naught, and it satisfies this property. And the way I did is I defined this formula and I chose the value of C such that these two conditions are satisfied, and hence I have a function f or a functional f which is defined from this space to my space of real numbers and satisfies this formula. And what is special about this whole proposition? Well, the special thing about it is earlier when my function was just defined on x naught, now it is defined on x naught direct sum the span of x. So I just, so as to say, enhanced the capability of my functional. I extended it. Earlier it was just defined on x naught and now it's defined on x naught direct sum span of x. Now I'm going to make use of this property so as to prove Hahn-Banach.